In this video, we're going to focus on the concept of impedance. What is impedance? Before we can answer that question, let's talk about resistance. So what does a resistor do in a circuit? A resistor opposes the flow of electrical current. Here's a symbol of a resistor, and the unit for resistance is ohms. Whenever you increase the resistance of a circuit, the current flowing in that circuit decreases. And so resistance provides opposition to the flow of DC current or direct current. It can also oppose the flow of AC current as well. Now, impedance is very similar to resistance. Impedance is represented by the letter Z, and like resistance, the unit is ohms. But impedance represents the opposition to the flow of electrical current in AC circuits as opposed to DC circuits. Now, the elements that impede the flow of AC current include the resistor, inductors, and capacitors. The opposition that a capacitor provides to the flow of AC current is known as capacitive reactance. The opposition of an inductor towards AC current is known as inductive reactance. Both capacitive reactance and inductive reactance are measured in the same unit as resistance, that is, in ohms. The formula for impedance is as follows. It's equal to the square root of R squared plus the square difference of the inductive reactance and the capacitive reactance. The inductive reactance is 2 pi times the frequency times the inductance. The capacitive reactance is 1 over 2 pi Fc. So what you need to know is that as the frequency increases, the inductive reactance increases while the capacitive reactance decreases. And as the frequency decreases, the reverse is true. So at high frequencies, inductors offer a very high impedance, and capacitors offer a very low impedance. At low frequencies, inductors offer or provide low impedance to the flow of AC circuit, whereas capacitors, they oppose low frequency signals. So capacitors have high impedance towards low frequency signals, and inductors have low impedance towards them. Now there is a middle ground, and this middle ground is known as the resonant frequency. At the resonant frequency, the inductive reactance is equal to the capacitive reactance. So thus the only impedance provided by the circuit is the resistance of the circuit. Now let's work on some example problems. So let's say we have an AC signal as the power source of this circuit, and it's connected to a resistor and a capacitor. Now let's say the capacitance is 5 microfarads and the resistance is 400 ohms. And we have a 60 Hz, 120 volt AC signal. Calculate the current flowing in this circuit. Feel free to pause the video if you want to. To calculate the current, we need to take the RMS voltage and divide it by the impedance of the circuit. So we have the RMS voltage, it's 120 volts. What we need to calculate is the impedance. And so we could use this formula to do so. Now, there are no inductors in a circuit, so XL is 0. But we need to calculate XC, the capacitive reactance. It's 1 over 2 pi times Fc. The frequency is 60 Hz, and the capacitance is 5 microfarads, which is 5 times 10 to the minus 6 farads. So the capacitive reactance is 530.5 ohms. So now that we have that, we can calculate the impedance of the circuit. So it's going to be the square root of 100 squared plus 0 minus 530.5 squared. So the impedance of the circuit is going to be 539.8 ohms. So most of the impedance of the circuit is due to the capacitor of the circuit. As we can see at low frequencies, the capacitor has a high reactance towards low frequency signals. Now that we know the impedance, we can now calculate the current in the circuit. So it's going to be the RMS voltage of 120 volts divided by the impedance. And so that's going to be 0.222 amps, which is 222 milliamps. So that's the current that's flowing in this circuit. Now for the sake of practice, let's work on another example. So this time, we're going to have three elements: a resistor, a capacitor, and we're going to introduce the inductor to it. So we have an RLC circuit. So the resistance is going to be 100 ohms, the capacitance 20 microfarads, and the inductance 200 millihenries. And this is going to be a 120 volt signal at the same frequency of 60 hertz. So go ahead and calculate the current that is flowing in this circuit. First, we need to calculate the capacitive reactance, and that's 1 over 2 pi times Fc. So it's 1 over 2 pi times the frequency of 60 hertz times 20 microfarads, or 20 times 10 to the 6 farads. And so that's going to be 132.6 ohms. Next, we need to calculate the inductive reactance, and that's 2 pi FL. So 2 pi times 60 times 200 millihenries, or 200 times 10 to the minus 3 henries. So then that's going to be 75.4 ohms. Now to calculate the impedance, we could use this formula. So it's going to be the square root of R squared, so that's 100 squared, plus XL, which is 75.4, minus XC, which is 132.6 squared. So you should get 115.2 ohms. So that is the impedance of the circuit. Now once you know the impedance, you can calculate the current. The current is going to be the RMS voltage divided by the impedance, and so it's going to be 120 volts divided by 115.2 ohms. And that's equal to 1.04 amps. So that is the current that is flowing in this particular circuit. Now let's calculate the frequency at which the inductive reactance equals the capacitive reactance. And as was mentioned before, that frequency is known as the resonant frequency. And it's equal to 1 over 2 pi times the square root of LC. So L is going to be 200 millihenries. So that's 200 times 10 to the minus 3, which is 0.2 henries. And then times the capacitance of 20 times 10 to the minus 6. So you should get 79.6 hertz. So at that frequency, XL will equal XC. So now you know how to determine the resonant frequency of an RLC circuit. You also know how to determine the impedance of the circuit and also the current that is flowing in the circuit. So that's it for this video. Thanks for watching.